Oh, hello, everyone. I hope you can hear me well. So I am Alex, and I'm a PhD student in ETH Zürich in the Scalable Parallel Computing Lab under the supervision of Professor Thorsten Heffler. So allow me also to express the hope that all of you and your families are healthy and will continue to be healthy. So we are in a bit of a strange and difficult times. However, it is great that this conference is happening in this online format. So now we have to see how this works exactly. So for my part, in order to minimize any potential issues, so last night actually recorded my presentation. So if you find this acceptable, I will play back the video and I will also provide the link. So if there is any issue, you can try also watching on YouTube if there is an issue with the platform. And of course, at the end, I will be here to answer your questions. So let me paste the link first. Okay, so this work is for last year's Gordon Bell Award. So what I want to show you here is that there is this scientific application called OMEN. So OMEN is a quantum transport solver. So this application has been in development for many years, actually, I think almost 20 actually, from the specialists in this area. So it has been already nominated before 2 times for the Gordon Bell Award. And last year it won with this work that I'm going to show you. So what we did is that we have what we call data-centric framework that we developed in the lab, and we used it to optimize OMEN. And we were able to achieve on the Summit supercomputer up to 2 orders of magnitude better performance. So let me guide you to the process of achieving those results. Let's start with some motivation. So electronic devices, from the servers in data centers to our smartphones, we use them every day, all day. So they are very important in our lives. Now, if we look inside these electronic devices, we will see that they have numerous electronic components. And in return, now these components, they consist of billions of nano devices, for example, nanotransistors. So therefore, it is very important that we continuously improve these nano devices so that our devices become over time faster, potentially smaller, and also more power efficient. So let me continue from this last point, and let's have a look at the CPU power density trends of the last few decades. So already more than 20 years ago, we achieved power density values that corresponds to a hot plate. And then shortly after, perhaps you have seen on the internet, you remember, that there were people making pranks and try to make the breakfast on top of CPUs because they were getting so hot. Now, if we had continued with the same trend, then we will have already surpassed values that can be found in a clear reactor. So obviously this cannot not happen because around the year 2005, we faced the end of Dennard scaling. So this started the so-called multi-core crisis, which was or is still an era of power-efficient multi-core processors that are unfortunately slower in sequential performance. So why did Dennard scaling end? It is because we started making transistors so small that quantum mechanical phenomena became dominant. So here on the left, I have the, let's say, drawing of a FinFET transistor. It's the fin of a FinFET transistor to be exact. So in the center in blue, it's the gate. Left and right, we have the source and the drain. And everything is wrapped around what we call a high K dielectric. Now, what we want to do is to actually look inside the channel of this fin and see what's going on. So the channel has what we call the conduction band edge. And then we also have the carriers of the current. So this can be electron or holes. For simplicity, from now on, let's only talk about electrons. Now, when the transistor is on, the electrons have high enough energy that is above the conduction band edge. So they can freely flow from the source to the drain of the transistor. Now, when the transistor is off, they have much lower energy. And the conduction band edge acts as a barrier. It does not allow them to cross the channel. However, due to quantum mechanics, there is a probability that an electron will be able to traverse the channel, to tunnel through. So this is what we call the source to drain tunneling. Now, so this is a natural phenomenon, so this is something that we already know. What the real problem is that as we make the transistor smaller, the same happens with the conduction band. So basically it becomes more narrow, and the probability for tunneling increases. And when we have tunneling, that means that we have leakage of current and increased heating of the material and all the problems that accompany this, essentially. Now, of course, we don't give up. So material scientists, semiconductor companies, they continuously try to come up with new transistor designs or new materials in order to solve the problem. However, they need our help. They need to be able to understand the characteristics of these transistors. So to be exact, what they need to know is what we call the characteristic curve of current and voltage at the gate. However, since we talked already about power efficiency, we really need to see how the material hits across the channel. And this way, the scientists can evaluate these new designs and see whether they can perform better than today's state-of-the-art transistors. Let's show also this was done from CSES. So how we can actually do now. So this is exactly how we can actually find these characteristics. So as with everything, either we have to build it and test it, or we can perhaps simulate it. And this is exactly what quantum transport simulation is. So let's see how this works. If we look again at the channel of the transistor, we have the electrons. And now each electron has some energy, but it also has another quality that we call momentum. So the momentum is basically an angle, and it's more or less the direction that the electron has while traversing the channel. Now, we can start with a simplified model where we make the assumption that the electrons do not interact with their surrounding. So when the transistor is on, they basically cross the channel, and they keep the same energy momentum. Nothing changes. So this is what we call the ballistic transport, and obviously it's not very accurate. Now, if we want to make a more accurate simulation, we have to actually forget about the above assumption and see what actually happens. So as the electrons traverse the channel, they may interact with some other particles that are called phonons. So phonons are basically the result of crystal vibrations and are responsible for the heating of the material. So what can happen is the electron absorbs a phonon and moves to a higher energy state, or emits one and moves to a lower one. And at the same time, it can change its momentum because the phonons also have a momentum. So this changes. And this is what we call the incoherent transport. So, okay, how we can do a quantum transfer simulation? So what is the workflow? So we start with a density functional theory application. So to be specific for this work, it was CP2K that was used. And we create the input parameters. So these are Hamiltonian and Hessian matrices. Now, a note about the use of density functional theory. This is because we need an ab initio model. So they are also empirical models that can be faster. However, the problem with them is they are not accurate enough for a simulation at the nano level. After we get our input parameters, we proceed with the actual OMEN application. So now this consists of two main components. The first component is called the non-equilibrium Green's function solver, so in short, NEGF. And this solver computes the density of the current. And then we have a Poisson solver, which computes electrostatic potential. And these components are executed in iteration until these values converge. Now, let me make a note about the runtime of the whole workflow. So the creation of the input parameters takes less than 1%. And also, these parameters may be reused for multiple simulations. So this can be further amortized. The Poisson solver takes a negligible amount of the runtime. So basically, the whole thing is happening on this NEGF solver. And this is why it was the focus of this work. So this is what we actually tried to optimize. Now let's have a look at the model that OMEN actually implements. And we are going to start with the main simulation parameters. And we are also going to see what values we would like for these parameters to have in order to make a state-of-the-art and very accurate simulation. So we start again, what OMEN does, it basically simulates a slice of this transistor because this structure is repeated for the whole height of the thing. So it's enough to simulate a slice. And now the exact size of the slice depends on the simulation we are doing. However, it's worth to note that for a state-of-the-art transistor, for the simulation to be realistic, then we want the width of the channel to be at least 4 nanometers. Now, in this slice, what we're simulating is a number of atoms. So this can be, again, for an accurate simulation, 10,000 or more. And then each atom has a number of neighbors that it interacts with, and we need to model. And ideally, we would like to have 30 or more. Now, for each atom, we actually need to simulate and model the electrons and the phonons that we talked about before. So for the electrons, these are modeled with the number of orbitals of the atoms. So typically, there are 10 or more. So for a silicon-based material, I think it's 12. And then we have 3 phonons. So this number 3 corresponds to the 3 degrees of freedom that the atom can vibrate in the crystallic structure. So what OMEN actually does, it makes 2 different versions of the slice. So there is one slice that has the electrons and one that has the phonons. And then we need to replicate those because we said that these particles have momentum. So we decide how many momentum points we want to simulate, ideally 20 or more. This is a very crucial parameter, both for accuracy, but also for computational and communication complexity, as we will see later. And then we saw that the electrons have energy, the phonons have frequencies. So we replicate the slices also for the number of electron energies, ideally 1,000 or more, and the phonon frequencies, which can be 50 or more for an accurate simulation. Now let's have a quick look at the mathematical formulation of the problem in order to see what exactly we are computing. So this NEGF solver has 2 main phases. So the first one is called Green's functions phase, GF for short. So basically, we compute what is these quantities that are called Green's functions. So we have a set of these G Green's functions for its energy, electron energy momentum point, and also a set of D, which is for the phonon frequencies and momentum points. And in this phase, we also compute the current that crosses the channel. Now, we take these Green's functions and we use them in the next phase, which is called scattering self-energies, where we compute the quantities of the same name. So here in the slides, it's these quantities where the symbol is the Greek capital sigma and pi. After we compute this, then we run again the Green's functions phase in order to get a more accurate estimation of the current. So as you can imagine, these 2 phases are executed one after the other until the value of the current converges. So now let's see how OMEN actually implements this. So we saw before that we have these slices that are replicated for the different energies and momentum. So OMEN creates 2 grids, let's say, and it's one for the electrons and one for the phonons. And then basically takes the compute resources that are available to it, like, for example, computing nodes in a supercomputer or a cluster, and assigns to them these slices. So I will give you a small example of how the original OMEN application does this. So we start, for example, the first node will be assigned 2 slices from the first momentum point. Then the next node will get the other 2, and the third node will get the last one from this first row. Then the 4th node will move to the next line, and this process continues. The same happens also for the phonons. And now let's see actually what is executed. So we start with the Green's functions phase. So what happens here is that the computation of the Green's functions is independently parallel for each slice. So there is no need for communication here. Only at the end, we need to compute the current, and we need a reduction for this. So this is a quite simple phase. Next, we have the scattering self-energy. So here things are a bit more complicated. So there is I call it a stencil-like pattern. Maybe you will disagree, but I will try to show you with an example of what goes on. So let's have a look at this dark blue slice in the middle of the electron grid. So what happens here is that we first select a phonon slice from the grid on the right. So for example, this dark red slice. And what we do here is the following. So we compute what will happen to the electrons of the dark blue slice if they absorbed or emitted the phonons from the dark red slice. And here we have two cases. And these are shown as an example, the two green slices now on the electron grid. So we take the data from the green and the red slices, we send them to the compute node that is responsible for the dark blue slice. There is a local computation happening there, and then some data is sent back to the node that is responsible for the phonon slice in dark red. Now this has to continue in rounds. So for example, next we take the other phonon slice that is below the first one, and we do the same thing. And we continue going in rounds until we cover the whole phonon grid. So essentially, for each electron slice, there is this kind of stencil-like communication that has size 2 times the number of momentum points times the number of frequencies. Now, if you put this all together for the whole electron grid, then we will see that basically we have computation and communication that is quadratic to the number of momentum points. And yeah, for computation, it's not easy to do this unless we change the algorithm completely of the simulation, which is not part of this work. But for communication, this can be a bottleneck, and maybe we can see we can do something about it. However, before we see why this is a bottleneck and some solutions, let's first have a look at what we consider to be a common pitfall for the development of scientific applications like OMEN. So if you want to create a scientific applications, usually you will assemble a team, let's say, of domain scientists and computer scientists, or what we call performance engineers. Now, of course, many times there can be a single person that does everything, and we call this person a computational scientist. However, even in this case, this person fulfills these two distinct roles. So while developing this application, what happens? The domain scientists are responsible for, let's say, the mathematical formulation of the problem, while the computer science and performance engineer are responsible for developing its application in a language suitable for HPC, like, for example, C++, and they also have to use required libraries for communication and use of accelerators. Now, the work of all these people goes into a single code base. And the problem is that as time passes and there are new algorithms and models implemented and optimizations on top of it, that this grows very large and can end up with what we call spaghetti code. And this is a problem because it's difficult to add new models, maintain the code, and also optimize it for emerging computing architectures of the future. So in order to solve this problem, we suggest the use of a framework that separates how these two roles, the domain scientist and the performance engineer, work. So what exactly is this data-centric framework? So we start with the domain scientist who comes up with a problem formulation. Now we expect the domain scientist to also write this formulation in a high-level program in a language like Python, for example, which is quite popular now with domain scientists. Then this high-level program that should be easy to write will automatically be converted in what we call a data-centric intermediate representation. Now, at this point, the performance engineer takes over, and this is a graph representation. So the performance engineer applies graph transformations in order to optimize the program. So we end up with a more optimized representation. And at the end, there are code generators that will generate optimized code for the target architectures. Like, for example, here you can see some CUDA code. And this is exactly what we did for the OMEN application. So we started with the original application, which has probably more than 50,000 lines of code. and we focused on this NEGF solver, which is about 16,000 lines of C++. And what we did is that we rewrote this using the data-centric framework in Python, and this took about 3,000 lines of code. And then we took performance-critical components of this Python implementation. We converted them to the data-centric representation. We optimized this representation, and we ended up with graphs that have approximately 2,000 nodes. Let's continue with the basic elements of this data-centric image representation, because I'm going to show a few graphs later, so hopefully they will be intuitive. So we have these oval shapes that we call access nodes, and they represent the data that are read and written in our application. Then we have these nodes that we call tasklets, and they are fine-grained stateless computations. However, they can also abstract away more complicated computational kernels. Next, we have data flow that is represented by the edges of the graph. And these edges have annotations called memlets that show the exact subset of the data that is being accessed at all levels. Next, we have states, the big blue rectangles, and these states can be connected by edges to create a state machine, and these edges cannot be annotated by control flow. And finally, another element, we have an abstraction for independently parallel computation. So you can see now in this graph, we have these two special nodes. We call them map entry and map exit. Together, they define a map, or what we call a map scope. So whatever is in this map scope is executed independently parallel as many times as it is shown in the index space of the map. So the index space here is the ij indices, and we have approximately m by n iterations. So for simplicity, perhaps you can also consider it to be more or less a parallel for loop. Let's have a look at how OMEN looks at a high level in this data-centric representation. So let me also use my laser pointer here. Maybe that will help a bit. So we said before that we have two phases. So we have one state for each of the phases. On the left, we have the Green's functions, and on the right, we have the scattering self-energies. Now, if we look on the left, we can see that we have two map scopes, and these correspond to the two grids, one for the electrons and one for the phonons, where we have this independently parallel computation of these Green's functions. Now, if you look at the indices of these maps, they go over the momentum and energy points. So they show that we have this independent computation per slice. Now, if we look on the right state, the scattering self-energies, you can see that we again have the same indices, but we have a couple of extra ones. So this A and B are basically the atom and neighbor dimensions. So here, in the data-centric representation, it's easy for the performance engineer to see that we actually have some extra parallelization that we didn't have in the previous phase. And perhaps we can use this to improve the performance of the application. So let's start and see what we can do. We are going to start with the first phase, the Green's functions. So here are two things. I now show you only the electron grid. You can imagine that whatever happens here happens also on the phonon grid. So for brevity, I cut it out. However, I added a few more details. So let's see exactly what's going on. Before, we only had this RGF kernel. But now what actually is going on here is what we have an initial Hamiltonian matrix. It goes into the map, and then we have a specialization of this matrix for its energy and momentum point. And we also compute some boundary conditions, again, independently for each slice. Now, what is interesting here is that the output of these two kernels here is actually independent of the iteration. So no matter how many times we execute this state, the output of this kernel should be the same for each slice. So obviously, you can ask this question. So if this is invariant, then why can't we compute it only once and then reuse the result? So with a data-centric transformation, we can do this exactly. So this will look like this. We create a new state that is executed once before we start the iteration over the two phases of the application. And in this state, we basically compute all the specialized Hamiltonian matrices and the boundary conditions. Now, this is not that simple, so there is a kind of a problem here with whatever resource constraints you have, especially in memory. So for some simulations that we will see later, these Hamiltonian matrices can basically be 3 gigabytes per energy momentum point, and the boundary conditions add another gigabyte on top of this. So as you can imagine, depending on how many computing nodes we have and how much memory we have, these transformations may be viable or maybe not. So in order to explore this, we also came up with some caching schemes. So the first one is obviously that we do not cache anything because we don't have memory. The other one is that we cache the boundary conditions, and the third one where we cache everything. So we will see later how this changes also the results. Next, another thing that we can easily do in the data-centric framework is that we can optimize operations by selecting different implementations for them. So here in specific, I have an example where we have sparse operation. So this is a code snippet from this RGF kernel that we saw in the previous slide. So what's going on here is that we multiply 3 matrices together. And this is a very common pattern in this kernel, where the middle matrix is dense, while the left and the right one are sparse and can be given either in CSR or CSC format. So now we want to see what's the best way to implement this. So we know already that for most architectures, there are already very optimized matrix multiplication kernels, so perhaps we want to use this. So in this case, it was on the Summit supercomputer, V100 GPUs, the NVIDIA libraries. We get very high performance. So we have some options here. So for example, we can use the GEM kernel from the Kublas library. So this is doing dense matrix multiplication. However, since we have sparse matrices, perhaps we can also consider the Q-sparse library. So we have 2 kernels here. It's this CSRMM. So this multiplies a CSR matrix on the left with a dense matrix on the right. And there is also this GEMI that multiplies a dense matrix on the left with a CSC matrix on the right. Now, we profile them for the different modes of operations. We can see that really the best time is if we can use the CSRMM kernel in NT operation. Now, based on this, we can come with some different approaches of how to actually perform this double multiplication. And for example, okay, the most naive approach will be to convert everything to dense and do dense matrix multiplication. However, we were able to find a scheme with some clever transpositions that we use to times the CSRMM kernel, and basically we can get a very big performance boost, as you can see. Another thing, so with the data-centric framework, it is easy to automatically extract parallelism. So here we have another code snippet in Python from this RGF kernel. So here, for a human at least, it's easy to see that we have these 2 multiplications that are independent. However, there is no annotation here. But when this is converted to the graph representation, then the framework can actually look at the graph and it can see that these operations are independent. So, for example, when we output GPU code, then the code generator can automatically assign these operations in different streams and also output the required synchronization code. So if there is the capability, maybe these operations can run in parallel. So here this is a screenshot from the NVIDIA profiler where we can see exactly this thing happening. Now let's proceed and see how we can optimize the second phase, the scattering self-energies. And here we want to show how we can optimize coarse-grained data movement, specifically this difficult stencil-like pattern that we saw in the previous slide. So first of all, we need to be able to model the communication that goes on in this phase. And we do this with tiling. So basically, this works as when you tile a for loop. So you take a map and you split it to 2 nested maps. And the outer map iterates over the tiles and perhaps your computing nodes, where you have assigned 1 tile to each one of them. And the inner map iterates over the single tile. So in other words, this is the workload of a single node. Now, what happens here is that these maps, here we have the map entries, they are connected by data flow edges that have the memlet annotation that we saw before. And the expression on this memlet shows us the subset of the data that are being accessed. So in other words, it gives us expressions for the surface of its tile. So this is the communication volume needed for each node in order to compute whatever is inside these map scopes. So we can take these expressions, and based on them, we can make a performance model and, for example, try to find the best tile sizes to minimize the communication or optimize it by any other metric. To see how this works, let's have a look at an example. This is what the original OMEN application does. So as we said before, so each computing node is assigned to a specific momentum point and gets a subset of the energies for this momentum point. And this leads to this high communication volume that is quadratic to the number of momentum points. So just to clarify, the quadratic factor is the number of electron momentum points times the number of phonon momentum points. So this is basically the same value. Now, with the data-centric framework, we can very easily test different decompositions by simply changing the tile sizes. So imagine that you have tiled all the dimensions, and by simply selecting the required tile sizes, you can test different versions. So for example, we could try to tile by atoms. So I will try to show you what happens in this case, how the communication will work. Let's assume that for simplicity, we have 4 computing nodes, and there is one slice assigned to each node. And then we tile these slices by atoms. And what we do is that with perhaps all-to-all operations, we rearrange during the scattering self-energies where these tiles are stored. And this allows each node then to compute the scattering self-energies without any further communication. Now, from a mathematical perspective, if we actually model this, we will see that this removes the quadratic factor, but perhaps some experimental results will be more convincing. So here, this is a chart of the communication volume per iteration in terabytes for a simulation that we will see later. So we change the number of momentum points from 3 to 11. And in the blue line, you can see it's the original OMEN application. And this is basically scaling quadratically. And in red is the data-centric version that uses an optimized decomposition. And we can see that it's essentially flat. Now, if we have a look at the last data point at 11 momentum points, the difference in communication volume approaches. Now, something important here, the takeaway should not be that the original OMEN application has a wrong decomposition, because there is no right and wrong, actually. So what you have is actually a better or worse decomposition based on your simulation parameters, but also on the machine that you are running the simulation on. So let me try to give an intuitive example here. So let's say that we have this better, let's say, decomposition, as I showed you in the previous slide, that is where we have this tiling by atoms. And we have a slice of 10,000 atoms, and we run this in a cluster with 100 nodes. So we have 100 atoms per node. So this is very good, super. However, let's say now that I want to do the same simulation on another machine, let's say the Summit supercomputer, which has 27,000 V100 GPUs. And now the problem is we have less atoms than the number of our computing nodes, essentially, which are the GPUs. So what we're going to do here, this doesn't work really. Well, it's simple. We go back and we find other tile sizes, again, with our model. So for example, I can tile by the atoms, but also by the energies. And perhaps I can find out that this is a better decomposition. So really, the point here is that we don't need to find the right answer, which potentially doesn't exist in the general case. We want to have flexibility. And this is what the data-centric framework allows for. Next, we can also optimize fine-grained data movement. So again, here, this is the scattering self-energies with a bit more detail. So I went into this map, and we can see that we have mainly 3 operations, like 2 matrix multiplication and an array scalar multiplication. And perhaps I want to focus on each of these operations separately and see how we can optimize this. So I can do map fission, which will break this map to 3, connected appropriately, of course. And I will focus now on the bottom part. So this is what it ends up like. And here it's interesting to see that we have a lot of very small size matrix multiplication. So these small matrices here are basically number of orbitals squared. So 10 by 10, 12 by 12. But what is interesting is that we don't want to get their individual products, but we want to sum them down. And perhaps we can do something here. Next, we can do data layout transformation. So we can rearrange how these matrices are stored in memory in order to get faster accesses. And then we can notice some patterns that we have rows of them that are multiplied by columns of them. And there is also a stride between these rows. And we can apply some clever linear algebra and perhaps combine those small matrix multiplication to a bigger kernel. Finally, we can put all of this together after we optimize all components separately and fuse the maps back together, and it will look like this. And now one more thing, I would like to focus now on this kernel that was exposed earlier. And we want to see what is the best implementation of it. So naturally, we will first look at libraries. So for example, we will check if there is something that we can do with the kublas library. There actually is an operation for that. It's the gem-strided bats. And we get some initial performance. Then we want to see if we can do better. So we actually try to do an all-the-way implementation with our framework without using a library. And we were able to get a performance improvement that is basically 7 times. This is because the sizes of these matrices and how it ends up, it's really not ideal for how the kublas library has implemented this operation. Now, as you probably know, the V100 GPUs, they have this tensor cores that they can do matrix multiplications very fast in mixed precision. So we also wanted to see if we can use this hardware, which might become prevalent in the future. And we actually did a version of this, of our kernel, and we got a further speed up of 5. Now, I want to make a comment here that in scientific applications, usually you need very high precision, like double precision. So you can't just say, OK, I used some mixed precision, it was fast, and it's OK. So we also tested this. So we actually looked at the inputs and outputs of this kernel. And we were able to create a normalization scheme and then experimentally show that this did not harm the accuracy of the output application. So we have approximately the same current values with acceptable precision, both when using the kernel in double precision and in mixed precision. So let's put everything together and see how the, let's say, new data-centric version of the application compares against the original one in C++. So we have a first simulation where we have a slice that is not very big. So it has a weight of only 2.1 nanometers. So we are far from the 4 nanometers that we said initially. And we have a bit less than 5,000 atoms. The number of neighbors 34, which is a good value. If the electron energies are about 700, which is a bit lacking. And the number of frequencies is 70, which is a good value. So first we did strong scaling tests with 7 momentum points. So this is a time versus the number of GPUs used on the summed supercomputer. In blue, it's the time for computation. And in red is the time for communication. So the 2 top lines is the original OMEN application, while the 2 bottom ones is the new data-centric version. So you can see that it's much faster. On the last data point, the speed up is about 17. Next, we did weak scaling test. So for this, we changed the number of momentum points from 3 to 11. And again, we have the 2 top lines being the original OMEN application, while the 2 bottom ones is the data-centric. Again, it's much faster. And at the last data point, the speed up is about 25. Now, this simulation is actually quite close to the limits of the original OMEN application. However, we wanted to do a better simulation, like a state-of-the-art accurate simulation for a realistically sized transistor with today's technologies, or perhaps those that we will have in the near future. So we did a second simulation where we increased the width to 4.8 nanometers, and also all other parameters, where what we said in the first slide, so a bit more than 10,000 atoms, and 21 momentum points, and also about 1,200 number of electron energies. So we run this up to the full extent of the Summit supercomputer. So in blue, it's using only double precision, while in red, we had this kernel that we talked before in mixed precision, so we get a bit better performance. We also use the different caching schemes here. So for the lowest number of GPUs, we didn't have a lot of memory available, so we didn't cache anything. For the next point, we cached the boundary conditions, and for the last two data points, we cached both the boundary conditions and the specialized Hamiltonian. Now, at the full extent of the Summit supercomputer, in double precision, we got about 85.5 petaflop per second, which is about 57.5 of the Limpar performance of the machine. And in mixed precision, we got almost 91 petaflop per second. Now, as we said before, though, this number of momentum points is really the bottleneck here. And it's basically what doesn't allow the original OMEN application to scale. So we wanted to somehow get a metric against the original OMEN application, but with 21 momentum points. So we did a third simulation here. We picked a very small slice that has only 1,000 atoms, but all the other parameters are the same as in the previous slide. So we ran this with the original OMEN application on almost 7,000 GPUs on the Summit supercomputer, and we compared it to the data-centric framework on the same number of GPUs, but on the previous simulation with 10,000 atoms. And we were able to see that the data-centric version simulated 10 times the atoms in less than a tenth of the runtime. So basically, the speedup was greater than 2 orders of magnitude. Okay, so let me now recap, and let's look at the conclusions. So we saw the heat dissipation issue that is a problem in nowadays computer architectures, and we saw that quantum transport simulation is a potential solution. It's a tool that can help us actually to find solutions. Then we saw a specific application that does this, OMEN, and we saw the domain scientist view, but also the data-centric view. And we saw how we can use this data-centric framework to optimize coarse-grained and fine-grained data flow, and also automatically extract parallelism. And finally, we saw that we were able to achieve great performance benefits. Now, for the future, for OMEN, the models already implemented in OMEN, they can be applied to other types of nano devices. So for example, apart from transistor, they can be applied in diodes. And as for the data-centric framework, the lessons learned can be applied to other scientific applications, and why not perhaps achieve similar performance benefits. So thank you, and I'm available for your questions.
Perhaps I will ask you the first question.
Mm-hmm.
In your model, I presume you use silicon and silicon oxide as materials of your transistor. How difficult would it be to run it for, let's say, gallium arsenide?
So basically not difficult at all. So we use the silicon-based material for the test because it was also much easier to also validate the results. So we made a new version of the application. We obviously checked the results against the original one, but it supports different material. So you basically, in your input, you basically have different inputs that correspond to the different materials, and the simulation works in the same way. Now, always I have to say that I'm not a domain scientist, I'm the computer science. So, but this is my understanding for working with this for quite some time. There is a question. So, how we can implement new computing architectures in the data-centric framework. So how this works is that the framework has different components. So it has front ends that you can write in different languages. It has the middle part, let's say, which is the representation, and we have the back end where we have the code generators. So if I understand your question, supporting a new computing architecture, like for example, let's say RISC-V, is basically writing a code generator for this application. It's basically creating, let's say, a plugin. So it's quite modular because the idea is that we can add different code generators in the future. So for now, perhaps if this was a follow-up questions, what we support is CPUs in general through C++. We have NVIDIA GPUs with CUDA, and we also support both Xilinx and Intel FPGAs. So yes, okay, we have a couple of questions. So for the first one, I will say that yes, we have other applications that we use this. I'm not sure to what degree I can talk, like, okay, you know, in Switzerland, we have CACS and Meteo Swiss, so we have collaborations with them. But so far, there is still nothing published, and so I'm also not responsible to immediately talk about them. But yes, they are stuff that we'll probably hear more about them in the future. The other question is, what is the language being used for the output code generation? So yeah, as I said before, so we output C++ for CPU and GPU. So for the GPU, it's CUDA code also. And for the FPGA, so it's HLS for Xilinx, and it's OpenCL for the Intel FPGAs.
Thank you very much, Alex, for your great talk.
You're welcome.
For the questions.